Welcome to lecture 30 of this course. Today we are going to study closure properties of decidable languages and Turing recognizable languages. Okay, so under some of the standard operations such as union, concatenation, star, intersection and complement. Okay. So let us create a summary table of the operations and the corresponding class of languages, and then we will see the proof of which of these classes are closed under which operations. Okay. So, let me create a table. So, we have operation, okay. Then we have decidable languages, and let us say we have Turing recognizable languages. Okay. So, TR stands for Turing recognizable. So, the first operation that we will see is union. So, are decidable languages and Turing recognizable languages closed under union. Okay. So, let us try to see. So, let us take two languages L1 and L2 which are decidable. Okay. So, L1 and L2 are decidable via halting Turing machines M1 and let us say M2 respectively. So, what can we say about L1 union L2? Is L1 and union L2 also decidable? So, the answer is yes, L1 union L2 is also decidable, and to prove this, observe that what we can do is that, so we can first given an input, okay, so given x, so let us say we have input x. So, what we can first do is simulate M1 on x. If it accepts, then accept, else simulate M2 on x. If M2 accepts, then accept, else reject. Okay. So, because both M1 and M2 are halting Turing machine, the design that we are giving here, so this is let us say design of a machine, let us call it M. So, this is let us say a Turing machine M. So, what will happen is that by this argument, the language of M would be equal to the language L1 union L2. Okay. Because M1 and M2 are halting Turing machines, M will always halt. If x belongs to either the language of M1 or the language of M2, then M would accept it, otherwise it would reject. Okay. So, this proves that decidable languages are closed under union. Now, what about Turing recognizable languages? So, can we do the same thing for Turing recognizable? So, suppose if x belonged to the language of M1, okay, then we were fine. But consider the following case, what if x is in L2, that is x belongs to the language of M2 and on M1 x loops forever, okay, it never stops. Okay. What happens? Then if we actually try to do this kind of a simulation, we run into a problem, because when I simulate M1 on x, it goes on forever, it never stops, although x actually belongs to L1 union L2, because it belongs to the language L2. Okay. So, actually we are never able to accept x using this machine M if we do this kind of a simulation. So, what is the idea? How can we modify the construction of the machine M so that it would accept every string that belongs to either L1 or L2. Okay. So, what we do is we modify the machine M in the following manner. So, given input x, what we will do is we will simultaneously run M1 and M2 on the input x. In other words, we will run M1 for one step on x, then we will run M2 for one step, then we again run M2 for one step, then again M2 for another step, and so on. Okay. We do not allow one machine to take control of x at a time. Okay. So, it is just that they simultaneously run the input x, and if one of the machines ever accept, then we accept. If none of the machines accept, or if both the machines go on infinite loop, then of course, we will go into an infinite loop, but it does not matter, because then what it implies is that x does not belong to L1 union L2. So, what we do is we simultaneously simulate M1 and M2 on x. Okay. In other words, if I write it in bracket, so run M1 for one step on x, then run M2 for one step on x, and so on. Okay. If either M1 or M2 accepts x, then accept. If both reject, then reject. Okay. And if both of them go into an infinite loop, or if one accepts, if one rejects and the other goes into an infinite loop, even then we do not do anything, we just go into an infinite loop, does not matter. So, in this manner, basically if we do this, then what we can say is that if L1 and L2, instead of being decidable, if they are Turing recognizable, okay, via halting machines M1 and M2 respectively, then this construction of machine M ensures that L of M is equal to L1 union L2. Okay. So, this proves that Turing recognizable languages are also closed under union. Okay. So, now let us look at the second property. The second property will be the concatenation operation. Okay. So, suppose L1 and L2. So, now what I will do is that for concatenation I will only prove it for Turing recognizable languages. The case of decidable languages is actually similar. So, suppose L1 and L2 are Turing recognizable via Turing machines M1 and M2 respectively. Then what we have is that we have that L1 is L of M1 and L2 is L of M2. Now, given input x, okay, I want to design a machine which would accept x if x is a concatenation of two strings, one belonging to L1 and the other belonging to L2. Okay. So, the idea is how do I guess this concatenation, how do I guess this dividing point of the string x, where x get divided into two parts, let us say x1 and x2, such that x1 belongs to L1 and x2 belongs to L2. So, to do this, what we do is that we will use non-determinism. I mean, of course, we can do this deterministically also, there are other algorithms also that one can design, but I am just going to give an application of non-determinism here. Okay. So, non-deterministically, partition x as x equals x1, x2. So, what do we mean by doing this non-deterministically? How do we write a non-deterministic algorithm that does this? So, what the non-deterministic algorithm will essentially do is that it will look at the length of x, okay. Let us say the length of x is maybe 85. What it will do is that it will just guess a number between 0 and 85. Okay. By guessing a number, it just basically guesses a sequence of binary symbols, such that the symbols basically give a number that is not more than 85. If it is more than 85, you can always discard. So, it will guess a number between 0 and the length of x, whatever it is, and then what it will do is that it will set x1 to be the string which is the first that many number of bits. Okay. So, let us say the guessed number is L. So, it will look at the first L bits of x and it will set x1 to be L. It will set x1 to be the string consisting of the first L bits of x, and it will set x2 to be the remainder part of the string. Okay. So, now once this is done, you simulate M1 on x1 if M1 rejects, then reject. If M1 accepts, then simulate M2 on x2. If M2 accepts, then accept, else reject. Okay. So, let us analyze this algorithm. When does this algorithm accept x? So, observe that this algorithm will accept x only in this step. Okay. So, only in this particular point it is accepting, no other place is it accepting. So, when does it accept? So, it is accepting first of all if M1 accepts the string x1, and secondly if M2 accepts the string x2. Okay. So, that means if x1 belongs to L1 and if x2 belongs to L2, that is the only case in which it is accepting. Okay. So, that is one side. Now, what if it is not? So, on the other side, if M1 rejects x1, then anyway we are directly rejecting, we are not even going into the third step. Okay. Or if M2 is rejecting x2, even then we are rejecting. Okay. So, that means if one of these two does not belong to L1 or L2, even then we are rejecting. A third case can occur if, let us say, one of them goes into an infinite loop on the corresponding string, that is M1 goes into an infinite loop on X1, even then we do not reach the third step, which means we actually do not accept X. Or if M2 does not, if M2 goes into an infinite loop on X2, even then we do not accept, which means that X is not accepted. Okay. So, the only case in which X is accepted is if there exists a point such that it can be divided into two parts, where both belongs to the corresponding languages. Okay. And in a similar manner, you can show if L1 and L2 are decidable, then L1 concatenated with L2 is decidable. So, what this shows is that L of the machine M, where M is this machine that we have designed. So, L of M is equal to L1 concatenated with L2. Okay. So, this shows that if I look at the concatenation operation, decidable and Turing recognizable languages are closed under it. Okay. Now, let us move on to the third operation, that is star. Okay. So, the star operation is also very similar to concatenation. It is basically concatenation of multiple strings from the same language. Okay. So, suppose if L1 is Turing recognizable, then via a Turing machine M1, what we do is that given input X, we first non-deterministically guess a number K, guess K partition of X as X equals X1, X2 up to Xk. So, this is the same. So, we just have one additional step here, where we guess a number K, and then we choose basically we do the same as concatenation, but instead of just guessing a partition consisting of two strings, we guess a partition consisting of K strings. Now, accept X if and well, let me not say if and only. So, I will accept X if okay. So, let me add a sentence here. So, simulate M1. So, this machine M1 on the strings X1, X2 up to Xk in sequence, and accept X if M1 accepts all the strings X1 through Xk. Okay, so, that is the only case where you accept. So, once again this is the design of the machine M, and what this gives is that L of M in this case is L1 star. Okay. So, this shows that under the star operation also, decidable and Turing recognizable languages are closed. So, once again, although for the star operation we showed the case of only Turing recognizable language, but the case of decidable language is actually similar, it is not any different. Okay. So, let us look at the fourth operation, that is intersection. Okay. So, what happens to intersection? So, remember that of course, regular languages are closed under intersection, but context free languages were not closed under intersection with context free languages. We only know that context free languages are closed under intersection with regular languages. So, what happens in the case of decidable and Turing recognizable languages? So, let us look at Turing recognizable. So, here actually it is the scenario is much better. So, suppose L1 and L2 are Turing recognizable via Turing machines M1 and M2 respectively. What we do is that we given an input x, we first simulate M1 on x. If M1 rejects, then reject. Next, if M1 accepts, we simulate M2 on x. If M2 accepts, then accept, else reject. Okay. So, once again observe that the only place where we accept the string x is over here. Okay. So, this is the only place where we accept. So, this is our design of a machine M. And suppose if M1 goes into an infinite loop. Okay. So, if M1 goes into an infinite loop, what it means is that x does not belong to L1, which means that it should not belong to the intersection of L1 intersection L2. Hence, we do not care, it just means that M1 the machine M also does not accept x, it goes into an infinite loop on x. So, in the case of intersection, actually we can afford to run the computation in series, okay, in sequence, so one after the other, okay, because here what is necessary is that if x has to be accepted by M, it must first be accepted by M1 and then it must be accepted by M2. Any other case x is basically either rejected or it goes into an infinite loop. Okay. So, this ensures that the language of M is L1 intersection L2. Of course, for decidable it is the same argument and it is much easier because both M1 and M2 are halting Turing machines. Okay. So, if you look at the intersection operation, both decidable and Turing recognizable languages are closed under them. Okay. So, now we look at the last operation for today, that is the complement operation, and here things get a little interesting. So, okay. So, suppose if L is decidable, via a halting Turing machine M, okay, how can we decide L complement? Okay. So, So, here we are assuming that it is, here we are only showing it for the class of decidable languages. So, suppose if L is decidable, then there is a halting Turing machine which accepts L, because if it, because we are assuming it is a deterministic Turing machine, there is a unique computation path. So, to accept L complement, we just have to flip the answer in the end. If M accepts, we reject; if M rejects, we accept. Okay. So, we just design a Turing machine which does the following. So, given input x, if so, simulate M on x, if M accepts, then reject, else accept. Okay. So, let us give this machine a name, let us say M prime. So, what this implies is that the language of M prime is nothing but L complement. But what we crucially use in this argument is that the machine M always halts, okay, because if M halts and accept, then we are rejecting; if M halts and reject, then we are accepting. But that is only true for decidable languages or halting Turing machines. What if L is a Turing recognizable language? Okay. So, for complement, decidable languages are certainly closed under complement, but as it turns out that Turing recognizable languages are not closed under complement. Okay. So, this is an exception. So, okay. In fact, we can say a little more, we can say something more about complement and Turing recognizable languages. So, I will state it as a theorem. So, L is decidable if and only if L is Turing recognizable and L complement is Turing recognizable. Okay. So, let me put it this way. So, L and L complement are Turing recognizable. Okay. So, what is the proof? So, suppose one direction is easy. If L is decidable, then of course, L is Turing recognizable, and if L is decidable, we just proved that L complement is decidable, which proves that L complement is Turing recognizable. Okay. So, hence the forward direction is easy. Now, what about the reverse direction? Suppose L and L complement are Turing recognizable. How does that imply that L is decidable? So, to do this, actually we construct a Turing machine, a halting Turing machine for L, which is along the similar lines of the construction of Turing machine for the union case, union of two Turing recognizable languages. Okay. So, what we do is that let us say that L is Turing recognizable via M and L complement is Turing recognizable via M prime. Okay. We construct a machine which does the following. So, simulate M on X if M accepts So, you simulate M on X and M prime on X simultaneously. Okay. So, again this is similar to the union as I said. So, you do one step of you simulate x on M for one step and then you simulate x on M prime for one step. Then again you go back to M, again you come to M prime and so on. If M accepts, then accept. If M prime rejects, if M, so M prime is for L complement. So, if M prime accepts, then reject. Okay. Now, observe that for every string either M will accept or M prime will accept, because every string either belongs to the language or its complement. So, either this guy accept or this guy accept. So, you will either be accepting or rejecting. So, on every string you always halt. Okay. So, and hence this is a halting Turing machine. So, this is a halting Turing machine for L, actually. Okay. So, I will stop here. Thank you.